Okay, we want to talk about normal curves. We've been talking about binomial curves. This is a binomial curve because it has separate bars in it, correct? Okay, so basically a normal curve is a continuous. It makes a continuous line like this, okay? So the more x's you have, and eventually it will become continuous, and it will be a smooth curve. Now, I will tell you that a normal curve is what you're going to see most often in real life, dealing with many, many things, and we'll get into that a little bit in a minute, okay? So the values of the binomial distribution approach those of a continuous function called the normal distribution. Many everyday sets of natural phenomena have approximately normal distributions, such as heights of people, annual rainfall, test scores. If you guys have ever heard of being put on a normal curve or a bell-shaped curve, that's what they're talking about.
Wait, do our finals get scored on curves?
It's not scored purposefully on a curve. What you're thinking about is changing it so the curve adjusts to your scores. But your scores naturally go into a curve. So naturally, most test scores are right around, say, 75 as the average. Okay? And then you're going to move your way out like this. So A's would probably be in this section of the curve.
Oh, this is the whole...
B's would be this section of the curve. C's are in this section of the curve. D's. In terms of amount of people that are in that section. Okay? So that's basically, naturally tests actually, when you're talking about average, most people fall in that average range. So if I give you a mean of how well you guys did on a test, then give one standard deviation away from that, top, above and below. That's where a lot of you are. We'll talk about that in a minute, okay?
Do we get to have a cheat sheet on the
All right, so a parent normal curve is the graph of f of x equals e to the, this is a negative x, you guys. It's negative x squared. And to be honest with you, this really is not that important to you at this moment. We're mostly looking at probabilities of dealing with a normal curve. Just so you know, that's just for your information. Yeah, to the negative x squared. Okay? The maximum value of this function is 1. And notice when that maximum function is, when is it? 0 is when x equals 0. Okay?
You can tell him it's 0.
Okay, so the max is 1, and it occurs right at the y-axis when time is 0, at the mean of being 0. Yeah.
Number 4. Exactly. They did the same thing right twice. Yeah.
No, one's to a negative infinity, one's to a positive infinity.
Oh. Yeah, I was like,
Okay, f is an even function so that the y-axis is the line of symmetry. You can see that it's a mirror image of itself based on the y-axis. Okay? The limit as x approaches infinity of f of x is 0. So as you go further and further to the right, this approaches 0 but never quite reaches it. Limit as x approaches negative infinity of f of x is also 0. So the further down you go on the x-axis, the closer you get to it, it approaches 0 there, but doesn't quite reach it. Okay? So that the x-axis is really an asymptote of the graph. Near the y-intercept, the graph is curved downward. Okay? So now look at this.
wait, can you go back up? Wait, why the word concave?
So it is concave down right here because it's like bending downward. But then it says further away from the y-axis, as you further away go south here, so to speak, or west actually, notice that it starts to curve upward. That is a concave up section right here. Right here is also a concave up section. And where it changes that direction is right here. That's called the inflection point. So from here to here, it's concave down. Further away from it, it's concave up. Yes?
What do you mean concave? Whatever happened to convex?
Yeah, this one's not even counting.
Wait, can you explain that whole thing you just said one more time?
Okay, so
Sorry.
concave, think of it as a cup. Okay? The part that holds water is upside down from here to here. Okay, so that's called concave down. The cup is facing down. Okay? Yep. And then concave up, the cup is facing up anywhere west of here or east of here.
So like.
Yeah. Yeah. These 2 points right here, this point right here and this point right here, are the inflection points.
How do we know where it is on the graph?
So at a normal graph for this function, the inflection points are at plus or minus 1 over square root of 2. Okay, that's just for the parent curve. Okay, so moving on.
Oh, hold on. Let me write that quick. Last one minus 1 over the square root of 2.
Yep, which is the same thing if we took that, and we don't like to leave a square root of 2 on the denominator. You can write it as plus or minus the square root of 2 over 2. That's the same thing.
Okay.
But for a standard normal curve, that's not the parent function. The parent function, again, is this. That's not a standard normal curve. It's just a normal curve. For a standard normal curve, the inflection points are at 1 and negative 1. So we get rid of those ugly fractions with the square root. Okay?
So that's what we're going to be using.
Yes. We're going to be looking at the standard normal curve. The area between the curve and the x-axis is 1, a total of 1 unit. Okay? It depicts the probability distribution of a standard distribution, which means a distribution with a mean of 0 and a standard deviation of 1. Okay? So, let's go back up to our curve just for a second. This area between here and here in a standard normal curve is 1. It's a total of 1. All right. Okay, we talked about this way back when we started talking about z-scores in first semester. You guys remember z-scores? Okay, so normal models tell us how extreme a value is by indicating how likely it is to find a value for for a value that far from the mean. Okay? So, for example, if the value falls within 1 standard deviation from the mean, then there's a 68% chance it will be there. Okay? If it's within 2 standard deviations from the mean, it's a 95% chance of that value falling between 2 and a 99.7% chance of falling within 3 standard deviations.
Okay, wait, can I try and explain it?
Okay, so here's your mean. Okay? We're going to call the mean at 0 because that's the middle of the line. Now, if you have a point that is like, say the standard deviation is literally 1. If we have a point somewhere in here that is, like, say, at 0.75, it's within 68% of the population. The whole population that's, say, we're talking about height of people. 68% of the population of people are within these two this standard deviation from here to here.
Are these the same numbers every?
We did this before, yes.
We did it.
We did this. Way back, we introduced this in first semester when we were talking about z-scores. So, remember, z-scores is your is the number of standard deviations it is away from the mean.
Yeah.
Okay? So, I'm going to show you an example, and I think with the example, it'll make more sense in a minute, okay? But basically, this is telling us the amount of the population that is between certain z-scores. Okay? So, for example, we have this lovely one here. The average height of 184 centimeters. with an average height of 184 centimeters, Dutch males are among the tallest in the world. If a normal model is appropriate and the standard deviation for the height is 8 centimeters, what percentage of Dutch men are over 2 meters tall? Okay, so what we need to do first of all is we know that our mu value is what? 184 centimeters, okay? Average height, okay? Now, we also know that the standard deviation for this is what? 8. Okay, 8 centimeters. It says it gave us that number. Now it says, what is the percentage of men that are over 2 meters tall? So I'm going to say A greater than 2 meters. How much is that in centimeters? 200. Now I wanted to place it in 200 because of the fact that we are in centimeters here. Okay, so how far is this 200 from our mean? Yep, it's 16 from our mean, which is, and as Anton said, we're going to take that 16 and divide it by 8 because we want to find out how many standard deviations it is from the mean. That's our z-score. So our z-score in this case is 2. Okay, so if we look at our map here, at 2, it says, what percentage of men are greater than that? We need to look and try to figure out how many men are in this shaded region.
Wait, what? 100 minus 99.7?
So, that's a good question. Is it 100 minus 99.7? Well, you notice that these percentages are always from one to the other. So the 68% is between these two bars. Okay? 95% is between these two bars.
100 minus 95. No, 99.7 minus 95.
So we need to find out, first of all, we know that we're going to go to this bar, right? So 95% at least. So we're going from here to here. That's 95%. Okay? We also know that 100 minus 95 gives us this section right here and this section right here. Do you guys see why I'm getting that?
Then you have to divide by 2.
Yes. So we just need to find this little section. So 100% minus 95 is 5%, correct? And that's for both of these tails together. We only want one tail, so how much is left? Divide it by 2.
What?
There's
You
2.
only want one side of it, not both.
Oh, they add up.
So 2.5%. So there's a 2.5% for men to be larger than 2 meters tall.
So, in inches, I'll wait it out.
This is in centimeters, actually. Suppose it takes you 20 minutes on average to drive to school with a standard deviation of 2 minutes. How often will you arrive to school in less than 22 minutes? How often will it take you more than 24 minutes? And do you think the distribution of driving times is unimodal and symmetric?
Yeah, wait, what?
Yeah, so we'll talk about that later. Let's do one step at a time, okay? So number 1, how often will you arrive to school in less than 22 minutes? What is our mu again? 20. Okay, and our standard deviation was 2. Okay, now it says how often will you drive less than 22 minutes? How much away from the mean is that? 2. Okay, so 2 is, yep, it's 2 away from the mean, so that happens to be 1 standard deviation or z-score of 1, right?
Wait, hold on, time out, back up. Don't you have to times it by something? You can times 2 by something?
Divide 2 by the standard deviation.
Oh,
Okay, so here we'll go back. So in other words, we had a difference of 2 from the mean, then taking 2 divided by 2 gave us a z-score of 1. Because that was the standard deviation. How many 2's away from the mean are we? We're 1, okay? So we have 1 standard deviation. If I were to draw a picture of our, here, I gotta do a better job than that. Okay. If I draw a picture of our curve, okay, we're saying that 22, which happens to be right here, is 1 z-score away from the mean, right? So what is the percent between 1 and 1? 68%. Okay, so 68%. All right, my next question for you is, we have that much, but we still need to include this tail in there. Because it says, what percent of the time are you less than 22 minutes?
So we have to subtract it from 100.
So 100 minus 68 is what? 32. Okay? And we only need half of that because we only want this half of the tail. So what is that? 16. So we have 16. So we have 68 total, and I'm going to add that little piece right there. That's going to be 16 plus 68. And the total of that ends up being...
Wait, is this, why are you adding 68 now? Why is it,
Because we know we need at least this right here.
wait, why do you know that?
We want to find out the shaded area total. Here, let me take a different color.
No,
Watch.
why didn't you do that in the last one?
Hold on.
I still don't really understand why we got 68.
I really
Okay,
don't
so...
understand.
Okay, so we have this right here already, right? We also want to add this part of the curve to it.
I don't know, but I don't even understand why do we have that already?
So more than 24 minutes. So let's look at our bell-shaped curve again. Okay, we know that our mean's at 20. 24 minutes is somewhere in here. How many standard deviations away from 20 is 24? 2, right? So we have 2 standard deviations away. So that being the case, what is the percent that is from here to the middle? It's 50%, right? Okay. What is the percent from here to here?
No, can you not do that? Can you not?
26.
95.
Okay, so 95 from here to here. Correct? We want to find out how often this area above it is.
So 2.5%.
Right, how did you get that, Monet? Actually, how much is the entire curve? 100. So 100 minus what?
95.
95 is 5, and then we only are taking one side of that tail.
Divided by 2.
Divided by 2. So only 2.5% of the time, yep, this time, will you take longer than 24 minutes. Okay, the last question on this. Do you think the distribution of driving times is unimodal? What does that mean?
Only one mode.
Only one mode. Is it unimodal?
No. Yep.
Yeah.
Yeah.
The mode here is at the maximum part, right? The most frequent. Okay, is it symmetric?
Yeah.
Yep. Both of those.
Wait.
Symmetric means it's like a mirror image.
So what does unimodal mean?
Means it has only one mode.